We discuss the power series. Okay, basically this portion um, I am not able to complete. I think I missed this topic. So Soel asked a question from this chapter. This is very easy, similar to your series. Okay, so let's have a look. It is just a small 10 minutes lecture. Okay, so what is power series? So basically power series looks like your some, like, what is your series basically this type of thing, right? And that summation an. So this looks like your a0. If you taking n equal to 0 to infinity, then it will start from a0, a1 plus a2 plus so on, right? Now power series, it is actually a function, you can say. This is looks like n into x to the power n, where n running from 0 to infinity. Okay, so this looks like a0 plus a1x plus a2x square plus a3x cube and so on. Okay, so this thing you can write as your function of x, right? So in this expression, basically if you choose some value of x, for example, if you say what is your f of 1, so you see this actually becomes this one, right? Okay, so then this will be just a normal series. So we can say, is this series is convergent? For example, if we consider 1, so it will be just summation n. So then the question is this series convergent or not, right? That we can check from the series chapter. There are multiple tests, right? Okay, instead of that, if you consider f of 2, this is becomes like a n into 2 to the power n, right? So same question, this is convergent or not. Okay, so here we have to say what are the ranges of x for which actually this power series is convergent. Okay, so that range you have to find. Okay, so that range is actually called the radius of convergent. Okay, so what is radius of convergent? So if your fx is equal to summation n x to the power n equal to 1 to infinity is convergent for all x belongs to minus r to r, then r is the radius of convergent. Okay, so there are some formula how to find the radius of convergent. Okay, before that, just take some example. Okay, so for example, if we consider fx is equal to just simple sequence n, suppose you are taking 2 to the power n, and this is you are taking x to the power n, right? So you can think that your n is your an is your 2 to the power n. This is your n term, right? So this power series, for which range it is convergent, you have to check. For example, if I say f1, so this is 2 to the power n, right? So obviously this is divergent, right? Because this is geometric series with ratio 2, r greater than 1, so this is divergent. So can you say for which ranges value this will convergent? So you see, if you take x belong to minus 1 by 2 to 1 by 2, for this range fx will convergent. You can take any number, for example f of 1 by 4. So what you will get basically 2 to the power n into 1 by 4 to the power n, right? So overall you are getting summation 1 by 2 to the power n. So this is obviously convergent. So in this way you can check. Okay, now I come to the point how to find the radius of convergent. Okay, so you learn this r you have to find, right? This r you have actually two theorem. Okay, so first one is called that if you have summation n x to the power n, n is running from 0 to infinity, then you have to find limit n tending to infinity a n. You have to take the mod and whole to the power 1 by n. This limit, suppose you are getting mu. Okay, so then you have two conditions, basically some property. If mu is 0, then the series is convergent for all x. Second, if 0 less than mu less than infinity, then convergent for mod x less than 1 by mu. Okay, and for mod x greater than 1 by mu. Okay, third, if mu equal to infinity, then it is nowhere convergent. Okay, so basically what you have to think, if you are getting mu, so you have to take r is equal to 1 by mu. That's the point. So you see, if your mu is equal to 0, okay, so then you, what is the range you are getting? Mod x less than r, right? That means mu equal to 0, that means mod x less than infinity. So that's why it is convergent for all x, right? If your mu is infinity, so 1 by infinity is 0, right? So that's why it is nowhere convergent. Okay, so in this way you have to remember. Okay, this is the thing. Okay, and one more theorem, the similar type. So you can think this is your root test type of theorem. Okay, one more thing you have. Oh, sorry. So here basically, instead of this root test, if you consider modulus of n plus 1 by n, okay, suppose this is mu, after that you have the all the thing is same. Okay, so then this is your another thing. So this is actually called the ratio test. This is basically ratio test, and earlier one, it is like root test, but this is a well-known theorem that is called Cauchy Hadamard theorem. Okay, proof is not needed. Okay, so one problem may come, and then you have to find just the radius of convergent. Okay, so for example, so I'll send me a question, this type of thing, I think, problem. Suppose you have x plus 2 square x square by 2 factorial plus 3q x cube by 3 factorial and so on. So what is your n here? N is your n square by n factorial, right? So here you see which one will applicable, like your earlier one. So you will see that second one will be more appropriate. Okay, so you just try to check limit n tending to infinity, n plus 1 by n. Okay, so what is your n plus 1? So n plus 1 square by n plus 1 factorial divided by n square by n factorial. Sorry, I think this is not square, this is n, right? Because this is also increasing. So this will be n plus 1, this will be n. Okay, so if you cancel this one, you have n plus 1, and 1 n plus 1 you can cancel, so overall you are getting so this is actually gives you 1 plus 1 by n whole to the power n, and you know this value is your actually e. Okay, so you can say radius of convergent, this is convergent for mod x less than 1 by e, and radius of convergent equal to 1 by e. Okay, so in this way you have to try. Okay, so you try this one as your homework, like x plus 2 factorial square by 4 factorial x square plus 3 factorial square by 6 factorial x cube plus 1. Find radius of convergent. So this chapter is in the SK Mappa book. I have sent you the earlier PDF, so you can have a look after 589, page number 589 onwards. You don't have to see the theorem, okay, just this type of example.